Okay, so our speaker today is Jennifer Ngadiuba, who's an associate scientist and a Wilson Fellow at Fermilab, and also a Fermi Forward joint appointment with Caltech. And she was a prize fellow at Caltech, leading at Caltech, and she's a leading experimentalist in high energy physics with a focus on cutting edge applications of AI at the CERN Large Hadron Collider. And one thing I found out while we were chatting is that while she was a postdoc here, she was never here because she was trapped at CERN during COVID and couldn't go anywhere. So this is the first time I met her. Her innovative work includes designing and deploying novel AI, ML tools for real-time data analysis and filtering for systems like CMS and Dune triggers, and developing the first deep neural network for real-time anomaly detection in the CMS trigger. She's a leader in the HEP community, serving as the L2 coordinator of the CMS machine learning group and contributing to the CERN Next Generation Trigger product. Jennifer's exceptional contributions have been recognized with significant honors, including the IUPAP Early Career Award. I think that was 2024, is that right?
Yeah.
Yeah. And an Early Career Fellow Award from Schmidt Futures. So let's welcome her. Okay, I got to give you this stuff. Oh, well, here's my glasses. You don't want that. Here's this. I think it's unmuted. And the microphone.
Yeah.
Okay.
Okay. Thank you so much for the introduction, and thanks a lot for inviting me here. It's a pleasure. I will talk about a specific application of AI, in part in high energy physics, and in particular particle colliders. So how we can use the AI to develop novel approaches in searches for to accelerate time to discovery. So in searches for new physics, in particular the LHC. So let's put things into context. The beginning of this century marked a big expansion of our knowledge of the universe, from the very small to the very large scale. And in particular, we had the discovery of the Higgs boson in 2012 at the LHC, which confirmed the standard model, and also the measurement of gravitational waves by the LIGO and Virgo collaborations, which confirmed the general relativity. There's still a lot we don't know. So the standard model, in particular, doesn't account for neutrino masses. Gravity is not included in the theory, and it explains only 5% of the universe, because there's no candidate for dark matter in the standard model, and also doesn't explain why there is everything at all, given that it doesn't account for the matter-antimatter asymmetry from the beginning of the universe. So to answer to these fundamental questions about the universe, we need to probe fundamental structure of nature. And to do that, we need complex experimental devices, large instrument structures, and big collaboration of thousands of people. So that's an example. We did the Large Hadron Collider, right? But also going more into the future, we expect upgrades of the LHC, but also big experiments that can measure neutrinos really, really precisely, like the Dune experiment, which is part Fermilab and part South Dakota, and also future colliders and so on, and also big sky surveys as well. So this comes with increasingly complex data, both in volume and dimensionality, which also comes with increasing need for efficient and accurate data processing pipelines or workflows. So here you can see, for example, the streaming data rates in terms of byte per second as a function of the latency requirements, and the different sizes represent how big the data sets are. So if we take LHC, it's particularly very challenging, because we're talking about big data size, big data volumes with very strict latency requirements, like in the nanoseconds or microseconds, in like high throughput, which is like even more competitive than industry standards, like if you compare with Google, for example. So this comes with challenges in simulating expectations for what experiments may observe, but it also requires innovative data and discovery-driven physics analysis approaches. So, as I said, like the LHC is probably one of the most, let's say, challenging in terms of dealing with big data. So it's located, it's a ring, right, located at CERN, part in Switzerland, part in France, where the proton beams collide at a very high frequency of 40 megahertz in different points along the rings, right? There can be 4 points at least. So we have each of these collisions where produce like thousands of particles. And then around each collision point, you have like a big experiment, which, like, for example, the Compact Muon Solenoid, which is what I'm part of, which have like about 1 billion readout channels used to detect all these 1,000 particles coming out of the collision. So we're dealing with data rates of petabyte per second. However, at the same time, collisions which produce interesting products, for example, an Higgs boson, are typically very rare. So the probability of producing a Higgs boson, it can be like 5 to 9 orders of magnitude smaller than producing only jets, which can be like, for example, our background. So expect new physics, like the answer to the questions that I just mentioned in the first slide, to be even more rare than that. So it's like really looking for a needle in a haystack. So this means also we don't have to keep all the collisions, right? All the events. So we have like a data reduction workflow in place at the LHC, where so we have like petabit per second of data coming out of the detector at 40 megahertz, which is right the collision frequency, and we do like a reconstruction, a very like coarse reconstruction of all this data in what we call the level 1 trigger, which is like our hardware trigger based on field programmable gate arrays. And why it's coarse? Well, because we have only microseconds to do that. So imagine petabit per second. We can buffer only for a limited amount of time before we can discard the event. So we have like really just a microsecond to decide if the event is interesting or not. So it's kind of a coarse reconstruction. But so this first level brings down the rates to tens of terabit per second, so at hundreds kilohertz. And then we have a second like layer, which is called high-level trigger, which further filters the events. But now there is more time because you already brought down the rate. So we have like 100 milliseconds latency. So you can actually do a nicer reconstruction here of the event and on CPU or GPUs because you don't have to be like microsecond fast. So this layer like brings down the rates further to tens of gigabit per second at 5 kilohertz. And these are the data that we actually like store offline. And then there we have plenty of time, to do the final reconstruction. But so at the end, we make physics discoveries, though, with 0.0025% of the events, while the rest is lost because we're discarding this in this process. So this works well. This works well when we know what to search for. For example, the Higgs boson, right, or some other motivated BSM theories. Usually we probe like tons of like BSM theories, the LHC. So in this case, like you have strong physics assumption that guide each step of the data analysis workflow, from indeed how you set up or like you engineer this data reduction to how you do the full data processing, and also how you engineer the final high-level feature statistical interpretation. So, so the problem, though, however, nature might be different from all of these theoretical models that we have in mind, right? And so, like the process that they just discussed maybe might not work because it might be that we're not looking in the right corner because we might have not imagined yet how new physics look like. that's why we want to really look at all corners. We try to look at all corners to like make sure that there is nothing that we're missing. And we can do that by, first of all, going back, looking at data with no signal hypothesis. Maybe remain surprised. And if we identify an anomalous signal, we can then formulate an alternative hypothesis, which then can be tested with new data and traditional techniques. So that's the approach that now we call anomaly detection. So today we can actually implement anomaly detection quite efficiently with AI. We've been using AI or machine learning, like in particle physics, since the 80s. It was shallow networks back then. But then over the last decade, there was a huge progress with technological breakthrough, which of course, like also us in science, we're we take it, bring it to our field and use it, and that's the area of deep learning, right? And so it's like we're starting using AI in many, let's say, problems, applied to many problems in particle physics right now. So it's nothing. So it's coming. It's keeps growing. So let's first with anomaly detection, which is like the focus of my talk. So we can use AI to do that, right? But what's anomaly detection? So in particular, you would like to identify some rare events in a data set which deviate significantly from the majority of the data and do not conform to a normal behavior. So let's say we can call the normal behavior a data region populated by standard model, and your anomaly is like your new BSM, beyond standard model physics. So the thing is that where AI comes into play is that you can actually model this normal behavior with a neural network. So we have started applying this to some physics cases, in particular to digit resonances. It will be clear in a moment why digit resonances are so cool. But let's take a step back first. So jets, first of all, are spray of hadrons initiated by some fundamental particle of some kind. So which can be a quark, a gluon, or also like a boson, standard model boson, so the top quark. And then so they spray, and then you cluster all these objects with some algorithm, and then so that's the final object. This clustered object is what you see, and these objects can have different properties depending indeed on the mother particle. So what we do at the LHC is jet tagging, which is basically identifying the mother particle. Oh, sorry. I just I pulled it. No, okay. Okay. So just a little bit of a step back also, before we reconstruct, so in order to reconstruct jets, we first need to reconstruct the particles, right, in the event. And we do this through the particle flow algorithm, which basically combines the information from many different subdetectors in order to tell if one is an electron, one is a photon, one is a muon, and so on. So we are actually really able to tell which particle, to identify each particle, so in the event. And then after that, we cluster them and make jets. So characterizing jets is a key task at the LHC because it can indicate new physics. So for example, there could be a BSM theory predicting a graviton or a radion, and this can actually decay into jets. And so if you know what's this jet, then you can tell if actually there was a new particle there. But also we can access with that standard model processes, so make precise measurements, which can then inform also new searches for new physics later. Or also it can also help us understanding the Higgs boson. So these jets indeed can have different characteristics, and be exploiting these characteristics can tell you a lot about the physics process. And also, but in particular, it can help you to suppress the background. So the background is mostly, let's say, something like this, one prong structure, we call it one prong, and a signal jet, which is rare, which is very rare. It can look, for example, like this with two structures or three structures, three-pronged structures, or it can have like displacement, like displacement in the detector, and that can tell you, for example, if it has some flavor. So we can, like the more like you go into understanding the particles inside the jet, like how they spread and what's their displacement, you can suppress the background and try to identify these ones. Okay, so we can do all that. And how do we typically do that? Let's say, or we have done it in the past, like in many years of since lab and first years of round 1 and round 2 of LHC, is that you you have, like, let's say, particle A, which is our digest resonance, which decays in two particles, B and C. You don't know these two particles, right? But you can also say, okay, let's assume these two particles, I know them. And so, like, for example, they can be a standard model particle. So you have a BSM particle A decaying in two standard model particles, B and C. So then you can do the completely supervised algorithm that tells you if B and C are compatible with some standard model particle. If that's true, then you reconstruct the invariant mass, okay? And then you look if the invariant mass actually is compatible with a resonance, then you get a bump here of the new resonance on the top of a smoothly falling standard model background. If you see that, then you claim a discovery, otherwise you set some crucial limits. So these are actually, so this physics case has been studied extensively indeed at colliders, as I just mentioned. You can look for two jets, and then you can start asking, are these B and C compatible with some particles, blah, blah. But by doing so, you can actually access like a huge, let's say, space of theoretical models. However, per each of these theoretical models, it's different. It's a different analysis, different paper. Okay, because the selections are completely different. So there could be many other possible BSM scenarios that are not covered by these dedicated searches, or there could be a BSM theory, like we never even thought of, right? So this case is kind of a natural place to explore novel analysis strategies. This is what we did with AI. So instead of assuming that B and C come from a standard model particle, you say, I don't know how they look like, right? I only know they don't look like the background. So you train a neural network to actually learn your standard model QCD background, and then you tag each jet as anomalous with no assumption on how it looks like. So like that, you would like to take every jet that is anomalous with respect to the standard model background. So how do we do that? So yeah, we're using AI, right? So we're going to design this anomaly detection search in which machine learning actually only enters in this part in which like we're training a model to actually learn the standard model background, but then the rest like is as usual. So you basically, you have your model and then you build some metric, okay, which you then like use like as a selection, and then you do the rest until the bump hunt. So the machine learning part is actually kind of like novel here, right? Because there's many different ways in which you can train the AI to identify anomalous jets. And dependently on how you do it, you can have more or less model dependence. So it depends how general you want to be. So you can be completely unsupervised. If you're completely unsupervised, you train your neural network really just on non-anomalous examples, so only on your background, okay? So that's the only thing you actually learn. And this can be done through autoencoders, in which basically you force information in a bottleneck. And then you reconstruct from the bottleneck, you reconstruct your training examples. So the network only learns to reconstruct that. And then it will fail at reconstructing exotic examples. So like if it sees something that is not standard model background, it's BSM, then it will not be able to reconstruct it. And so it will give rise to a very high anomaly score, which can be like what we call the reconstruction loss. So that's your like a red fish. Or you can, so that's completely unsupervised. So it only knows the background. Now you can do it weakly supervised, which is like, it starts having a little bit of some assumptions. In fact, so in a typically fully supervised strategy, you train on pure Monte Carlo signal and background. So you have your labels. So you know what's signal, you know what's background, fully supervised. However, like if you want to train, like for example, on just data, you don't have these labels. So you can actually invent this weak supervision strategy, in which you make an assumption that you have your data, and some part of the data has more contamination of signal, and the other part of the data has less contamination. But this is an assumption, okay? So the idea is that if your assumption is correct and is following nature, and it's what nature is following, then your classifier, so your neural network, will enhance your signal population. So, and then finally, you can also go through a more like semi-supervised, which have even like more model dependence, because you actually use full Monte Carlo, and you inject actually the signal simulation in your classifier. So you're basically saying, like you can actually train the neural network saying, okay, if there is like a signal, it will look a little bit like this. And so if there are other signals that are similar, then still the network will be able to disentangle the two from the two, like to separate it from background, just because you injected some knowledge of what the signal will look like. Of course, if the signal doesn't look like that in nature, then it's wrong. So we've been doing R&D on these methods on toy data sets already since 2019, I would say. So there's been like, these are some examples, but there is way more of that. And we started seeing it in action only a little bit later. In particular, for example, here you can see different methods that have been explored. You want to, let's say, understand the, let's say, the potential, the discovery potential of these methods. So, for example, you can inject anomalies of varying production rate or cross sections in some background simulation, and then calculate the discovery sensitivity metric, which is what we call the p-value, right? And you can compare all our anomaly detection methods with instead dedicated searches or traditional searches, and then we have like a huge improvement in discovery probability when using anomaly detection, depending, of course, on how probable or how rare your event is in your data. Okay, there is always that dependency. So these are very powerful, and they're very powerful because they generalize. So this is like just one specific simulated signal, okay, that we're testing. If I show you others, the situation is the same. So it really generalizes to many different signals. So that's the cool part. Yeah.
Any examples where you introduce an anomaly and it just fails? It can't find it.
Well, yeah, it can. I mean, it can like misunderstand an anomalous event for a background event. Of course, this always happens. Depends also on the reconstruction. For example, the reconstruction also has its failures, right? You might have also maybe some, like you could have lost one jet. You didn't reconstruct, or you misreconstructed. Always error.
The reason I asked the question is a long time ago. Now there was a colloquium on using machine learning for doing math, and you train it on a set of numbers of a certain size, and it could do manipulations, arithmetic, on those numbers. Examples not in the training of the data, but then when you read numbers of a bigger size, it just completely failed. But there's nothing like that here that you know this.
No, I'm maybe more concerned about like the other way around, like hallucinations, right? So, because that's what I would be concerned for. Like if I like inventing signals that do not exist, and you cannot even interpret it. So sometimes these are black boxes, right? The more like we go into big models, the more it's black boxes. It's very hard to interpret, so you don't know if it's been an hallucination or not. Any other questions? Sorry, I didn't interrupt, but you can interrupt me, yeah, anytime. So if there are questions, comments. Okay. Yeah, okay, so we started applying to LHC data, okay, this method, hoping that there is at least no hallucinations, first of all. And I mean, if we find one, probably if we find an hallucination, we're gonna like publish in 2030 or something like that because we have to scrutinize everything. But okay, so we haven't seen hallucinations and we haven't seen discoveries. We just set exclusion limits basically so far. Although like it kind of can be tricky to set exclusion limits here because to me it's like anomaly detection is more like a way to like kind of like a discovery method rather than a method to set limits. But we still do that. It's hard to reinterpret the limits and so on, depending. We can discuss that later. But in particular, so there are like 3 Atlas searches and 1 CMS search, which I contributed to. And why there is just 1 CMS search and like many Atlas ones? Well, it's because in CMS we actually probe many different methods. So all the methods I discussed so far, from unsupervised to wiki supervised to semi-supervised, like we have been testing them all. So it's like 5 different. So it's actually, sorry, 5 different methods, and we test them all and compare them in 1 paper. So it's mostly like basically many different analyses. So also like not only they differ in terms of like model dependence and learning approach, but also in terms of input features. So like we use like, from just very, very basic input features, like very unbiased, to input features and instead start having like, some supervision in it. So like, start putting some high level features that can help identify some type of signals, which means like becomes less and less general, the more you go here. So it's a nice complementarity. So I think it was very useful. Now, let me get a little bit more into another part of this, let's say, of this story. So I talked about the data reduction workflow at the LHC, right? So I have these triggers. So the level 1 trigger rejects 99.75% of the events, and high level trigger 99%. So at the end, we discard a lot of events, right? So is new physics even there? Like when we just select all that little fraction and consider that event filtering starts really, really early in the data processing, in a place in which we have so little time, like microseconds, in which we cannot even do like a full reconstruction of the event, right? We do something like kind of like course, and then we put some thresholds. Like you can put a threshold, for example, on the energy of the jet or of the event, and maybe if you're lucky, new physics is here, but maybe like new physics is like just below this cut, right? And then you've lost it, just because of some assumptions that you're putting here. So we started thinking how to address the challenge as early as possible in this data reduction workflow, and in particular the level 1 trigger. And that's particularly challenging because neural networks can become very, very large, which means that memory and number of operations required for the inference of the neural network can easily explode. And here we have strict constraints. We have latencies over microseconds. We need to use FPGA hardware. So it's not like you always have tools to actually do that, to do machine learning on FPGAs. And also has scarce resources. So it's not that you have like, 10 boards, 10 chips only for you. There's other stuff going on here, right? You need to make the objects, you need to calibrate the sensors and stuff like that. So there's a bunch of stuff here. So you can only count on a very tiny part of the system. So how do we fit a neural network here? Well, so as physicists, like many years ago, we started building like this tool, high-level synthesis for machine learning, Fermilab, which is a tool to efficiently program the FPGA hardware for neural networks with some experimental constraints in mind. So we built it, we started mostly physicists when we started this project. Then it became huge with many other people working on it, like electronic engineers, computer scientists, and so on. But the main idea is that you start with a machine learning model specified in keras or TensorFlow or or PyTorch. And there is a highly optimized code here, which we wrote in HLS, high level synthesis, which is mostly like kind of a C++ code, just like very, very optimized. And then you convert the model through HLS to an actual firmware that then you can just deploy on your FPGA, right? And plug it in your experimental system. And now like how the optimization here goes is very customizable. So you can like put, so you actually, yeah, you can go here and look at tutorials and stuff like that. But it's very user-friendly. You can actually customize and say, yeah, I want to this latency in mind or this other latency, these resources and so on. So how does this customization or optimization works? Well, first of all, a neural network inference is just matrix multiplication, right? So an efficient implementation on FPGA like uses digital signal processors, DSPs, and you don't have an infinite amount of DSPs on an FPGA like you have on GPUs, right? Comparison. So you might have like maybe 10K DSPs in a modern FPGA. So if your basically, if your network has a lot of these multiplications, it's gonna be hard to fit. So you need to play some tricks. So something we discussed, we as I learned a lot about is compression or pruning, in which you can train the neural network by in a way that it starts sparsifying the multiplications, and we find that by doing that iteratively, like basically you start like removing some weights, some connections, you realize that there is a lot of redundancy in the network. You don't need to keep all the connections. You can just start removing some. Like for example, here we show that you can remove like up to 70%, and the number of DSPs, of course, like is reduced by 70% because you're basically zeroing the multiplications. And at the same time, we keep the same accuracy, or maybe like you lose maybe like a few, just really a percent also. So this is a very powerful tool. Another powerful tool is to work on quantization, in which instead of using floating point, which is not very efficient on FPGAs, you actually reduce to some like a certain number of bits. We call it this like fixed bit represent a fixed precision, in which you can set both the like the number of integer bits and the number of fractional bits. And then like, of course, there is, if you do it after training, you have to pay some penalty at some point. For example, like if you start like reducing the number of bits too much, then you start losing accuracy, for example, here. Okay, so you need to be careful. Now you can also like work on a parallelization. So FPGAs are really good at parallelizing. So for example, if you want to do 4 multiplications, you can do like all four simultaneously and use 4 DSPs, or you can instead start parallelizing, serializing, and then you use less, but it will take longer. Okay, so you can see this, for example, here. The more you basically you parallelize, the shorter is the latency. And if you start like serializing, then you have longer latency. And at the same time, you need to be careful with the number of DSPs. The more you parallelize, the more is the number of DSPs, and then if you serialize, then you use less, but then it's longer latency. So there's a trade-off. Now, there's also like other things we've been studied a lot. So I discussed like I just said about fixed point precision, right? Like about quantization. So you train in floating point, and then you quantize, and you start losing accuracy. But instead, what you could do better is quantization while training. So you actually like fix the precision during training, the precision that you want. Okay, so this means that your loss. Again. Sorry. It basically means that your loss minimizes knowing which precision you're using. So, and actually this is very powerful. So you can see it here. So that's the accuracy, okay? This is the number of bits. And if I do post-training quantization, I lose accuracy like already here, right? But if I instead put the accuracy in the training so that it's aware of the quantization, then I keep it like, I keep the accuracy up until like maybe 2 bits even, so which is really, really low. In fact, like with 2 bits, like, okay, you can go here, like, see, look at the DSPs, and the DSP is like in the range between 4 and 6, or even less than 4 bits. It's like nothing. So you can really, really reduce the size of your network and still keep the accuracy up. So it's amazing. Now, you can squeeze even more performance if you do high granularity quantization. So in particular, so what I just showed before, so here, sorry if I didn't mention, we've been using here Google Q-Keras, which is like was our first tool that we bundled it with HLS Fermilab. But then with time, we understood that Q-Keras was like, I mean, it's good, but it has some limitations. So for example, you can only quantize layer by layer. And also, you need to scan the number of bits. So like it's not included. So you can say, okay, now train with 10 bits, and then with 5, then with 3, and then you decide which number of bits you want to use. Okay. So it becomes an hyperparameter, actually, hyperparameter. So instead, what you would like to do is to first optimize the bit width of each neuron, first of all, and you want to do it like in the gradient descent. So like you want to do it automatically, that you don't have to scan. You don't have to scan it. So we started working on this package, high granularity quantization. As a work, actually, we worked this with a Caltech student, Chang, in Maria's group. And so here, like you can access the code. So the idea is that basically the bit width is a continuous variable, and this can be achieved through some surrogate gradients in which the bit width is actually becoming an optimizable parameter through gradient descent. And this means also that pruning it's automatically integrated because some neurons will just want to go to 0 bits, so they just want to go to 0. So you don't even have to scan that part either. So it's really, it can really squeeze performance, and you can see it here. So like you can actually like compare HGQ with Q-Keras, which is what we had before. So these Q-Keras, these are the resources, and actually similar resources, you can actually have higher accuracy using HGQ at the same resource. So it's very powerful. Now, so let's go back to anomaly detection. And we said, like, right, we have anomaly detection offline on digit resonances, but then we want to bring it to the trigger. So we put together all these tools I discussed. And we want to implement this in the trigger system, and we did that for this latest run 3. In fact, the idea though here is that we don't want to focus only on jets, but we actually want to focus on the full event, right? Because you want to check, like, you want to make sure that your event, it's not discarded and it's still anomalous. So we can do that in the trigger because we have, what time is it, by the way? Am I? Okay, still have time. Still have time. Other questions, by the way? Haven't. Okay. Okay, so we want to identify in the trigger system, so in the level 1 trigger, if an event is anomalous or not. And we have all the information. Okay, so like a rough reconstruction, but we still have the information. So we can like look at the muons, at the number of muons, or at the energy and number of muons. We can look at also the calorimeter objects, which are like, jets, electron photons, taus, energy sums, and so on. And these are usually the inputs to the global trigger. And so the global trigger has access to all these basic event objects and typically implements. I need to stop doing this. Okay, yeah. So yeah, so these are the basically subsystems of muons and calorimeter objects, and they make the objects, send them to the global trigger, and then the global trigger like implements like some topology, some topological identification. So for example, I don't know, like, is there one muon with PT about 22 GeV, or are there 3 muons plus the invariant masses and stuff like that? So you try, like here, to implement a menu that is sensitive to most of the standard model physics and the BSM physics that we have in mind. So we want to, what we started thinking about it indeed is to complement this with anomaly detection. So in a way that, you add more, you start like going in some corners of the phase space that you haven't thought of. So in CMS, we've done this, and in 2024, so in the 2024 data taking, CMS established this new trigger paradigm with sub-microsecond autoencoders for anomaly detection. So what do? Is like we do it fully unsupervised, so with an autoencoder, actually a variation autoencoder, which takes as input the full information about the event. So like if there are muons, so which energy, which position, and so on. So we take the full vectors of all the objects, and also the missing transverse energy, which is like an information also back the full event. And from this, we build an anomaly score. Okay, and then we decide, we put some thresholds on this anomaly score and select, let's basically save offline only the events that pass this anomaly score. Now we set different thresholds based on the trigger rates that the CMS collaboration decided to give us. So we had to tune a little bit. So right now, so we started this in 2024. We took data also this year, and we are in the 250 Hertz pure rate. Okay. Okay. So, but the cool thing also here is that we call this Axolito. Of course, we branded it. Stands for Anomaly Extraction on Live Level 1 Trigger Algorithm. It's cute animal, so it was fun. And we synthesize it. So first you train it offline. You do quantization-aware training. You do high granularity quantization. All those stuff. Convert it through HLS for ML. And plug it in the board, the FPGA board of the system, of the actual system. So you see actually that's like the actual, like how the board is occupied by other stuff. And then our, in violet here, our Axolito. It's very tiny. It runs in 50 nanoseconds, and it basically uses very little resources because of the quantization-aware training. So that's why we're able to do that. And also HLS for ML, like really, really super optimized this, so to make this happen. Okay, so a little bit of a timeline. So we started, so HLS for ML was first released in March 2018. That's our first paper. That's when I was, not even 1 year CERN fellow after my PhD. And took like 5 years basically to get the first machine learning model inside CMS in the level 1 trigger. So I've been like in between this and that, it was like a lot of stuff. And it was not bad. Like it was way more complicated than I thought. But okay, so in between that, so we started taking data with what we call Axolito V3, which is like this simple autoencoder I just said in May 2024, so at the beginning of data taking. Then we upgraded to V4 model in August, which is SV3 in architectural point of view, but retrained on new data, because you can imagine you're doing anomaly detection, so you kind of like want to make sure you don't detect spurious anomalies or hallucinating, right? Just because your data is just slightly different. Then also we had those another algorithm like developed by Princeton, which uses the calorimeter only. And then this year we upgraded to V5, which I'm gonna tell you a few details in a minute. And then also in May this year, Atlas also started taking data with their own anomaly detection trigger. It's like 1 year later. So now it's time, like between Atlas and CMS, to talk and see what we learned. Okay, so just one thing, as I said, like our baseline was like a variation autoencoder, but then we started moving a little bit farther from it. So that brought to Axolito V5, which took data this year. It's a little bit more performant. It uses contrastive learning. It's like, it's something new, like brings architectural improvement because it actually gives like a latent space that is more expressive by basically encoding some augmentations. So you would like to basically tell the network that certain augmentation of your data, they actually should kind of look the same. Here's the full formula. We can go later towards that. But yeah, so for example, you can do some Gaussian smearing or objects masking, which are like normal detector augmentations. Like you might lose like a muon because like one muon chamber is gone, or you can have like different calibrations. So these are your augmentations, but you want to tell your network that those events are actually the same. And that's how we train the backbone, what we call the backbone frozen. And then downstream, you build a like very powerful representation. And then downstream, you can do an autoencoder at the end. So these are some of the physics performance. These are many different signals that we looked at, as benchmark. So we are sensitive to a variety of signals with jets, with leptons, with forward jets. So it's like many different topologies. And then like comparing the different lines is basically comparing the V4 models, which was the baseline autoencoder, to the new model, and with some increase in performance. And also what's cool is that in some cases, like we see how our anomaly detection gives more signal efficiency than some algorithms in the standard menu. So that's kind of interesting. Then we started also looking into like interpreting why these events are anomalous for the network, right? So like, for example, this is still a work in progress in some sense, but we can already get some glimpse, some understanding of it. So like we see like how we are basically triggering on events with low energy and high multiplicity. So if theorists like have ideas on what can be like, the low energy and high multiplicity, that would be cool to explore like as a benchmark. But definitely there are already ideas, like for example, swaps, like some type of very, very non-standard events. This is actually one example of the most anomalous event that we triggered in 2023, which is not triggered by anything else. So it could look like something like a swap, for example. So like high multiplicity, not clustered events. So there would be more to do in terms of like doing the full interpretation of the degree of anomalies. And we're also like designing now like a full physics analysis, which is in progress. Another cool thing is that as a validation, we've looked at the dimuon resonances. And so like you can see how like after triggering with axolotl, we can actually see basically like the Z peak and the J psi and different dimuon resonances. So meaning that axolotl actually can see these events as anomalous, which makes sense because we're basically training only on pileup or like on jets on QCD.
They're standard model events, right?
Yes. But the training data set is mostly QCD. Yeah, exactly. So the fact that we can see as anomalies like muons, it makes sense. If we wouldn't, then it would be a problem, I would say. Okay, so like I'm just like going like now, fully I have still 5 more minutes to discuss a little bit more of an outlook, of a look into the future. So we're going to upgrade CMS for high luminosity LHC, right? Because at high luminosity LHC we expect like 200 pileup interactions. So like now we have like about 60 collisions per bunch crossing. So like 1,000 particles. Then like when you start going to Illumi with 200 collisions per bunch cross, you start having like way more particles. And then that's why we build more granular detectors, but also means we need to upgrade the trigger as well, because it needs to cope with this, right? We cannot use the same system we're using now. So what happens is that CMS will upgrade both the level 1 trigger, of course, and the HLT to enable to do the same physics, but at higher pileup. And to do that, what's the best? Like trying to bring more of the offline reconstruction online. So we're going to do particle flow, which I discussed before. So when we put together all the detectors, all the subdetectors to make to build each particle. But that's not trivial. I mean, to do that, you need tracking. You actually need like the internal silicon detectors to be able to run in real time at 40 megahertz. So that was the game changer, the tracking, because the calorimeters was already there, but the tracking was the game changer. And then we have now what is called the correlator trigger, where we put together tracking and calorimeter, and we actually do particle reconstruction at 40 megahertz. This is huge. This is also, we're able to do that also because we're going to have more time. So right now we have 4 microseconds to run the full trigger, but in the future we're going to have 12.5 microseconds. So that's three times longer time. Still a little, but with the more board, like the boards, also FPGA boards, like they upgraded over the years, right? So now we have more powerful boards, more time, so we can do more here. And we can try to use all this granular information, like really the information of each particle. So we expect machine learning to be well embedded into the level 1 trigger for phase 2 and to exploit this higher information granularity. And we have like about maybe now 20 projects between neural networks and BDTs in development, accounting for like 25 billion machine learning inference per second. So there's a lot going on here since the actual technical design report has been way more. So that's something I'm actively working on. So in particular, I would like to build here in the correlator where all the particles are available. I can do anomaly detection here, right? Now, with using like like using machine learning and using all the information of the event, like actually all the particles. So it's actually, yeah. So in some sense, it's not trivial. But not only anomaly detection, actually. I could like build an embedding here, right? Like a powerful expressive latent space. And then I can do offline with this let's say, not offline, but downstream with this the latent space. I can do whatever I want. I can do anomaly detection, or I can do like any other type of event level identification. So that's what we're trying to do towards, like, let's say, an ultra-fast foundation model where you build this in this expressive latent space, and then, like, downstream, you can do, like, many different things, not only, like, triggering, but, I mean, here in this case, it's triggering, but also more like robustness, but I will talk in a second. So what I want to say is that to do this development, we worked on a data set, which we called it Collide 2View, which is the first ever data set that has with a realistic pile-up condition and for phase 2, and also with this level 1 trigger-like objects, so smearing, quantization, and all that. To view, because it also has the actual offline representation as well. So it has, for each event, it has 2 representations, one level 1 trigger and one for the offline. It has like 1 billion events. It includes many different processes, standard model processes, like a huge number of standard model processes, as many as we can think of, plus some BSM processes to test anomaly detection, for example. So the idea is that you would like to start, instead of training only on data, you want to start injecting, using Monte Carlo for these trainings, in order to build a more physics-informed later representation that can be used indeed for many different event-level tasks downstream. So, like, for example, you can imagine like encoding, this is like TT bar, DX2 for B, with some vector boson fusion. So many different, like, let's say, imagine that each standard model process has its own blob here. So that's a very expressive latent space. You can use it then also for anomaly detection, but also for actually identifying some standard model processes of interest. So that's something also I'm working on with students here at Caltech. We started this with Ryan, who just started here, and Zishun is also now contributing to the implementation of this idea for the level 1 trigger for phase 2. So yeah, sorry, one last thing I wanted to say is that like typically you want to use transformers, which are state of the art nowadays, right? But actually like they can be very tricky to be implemented on FPGAs because they use like a lot of computation and not fast. So there's some work we're doing here also like in speeding up those and also like identifying more efficient architectures like MLP mixers, which like that's something else I'm working on. I worked on with a student here at Caltech. And finally, adaptability and robustness is also something that we need to keep in mind in the future, right? Because once you start having like all these machine learning models in the trigger, and maybe they're all like concatenated as well, you want to be as robust as possible. So in a way that you don't have, or either you have a way to recalibrate it quickly, and bookkeeping also the recalibration, like we do with normal calibration, or you actually can develop very robust pre-training strategies. And other things I'm working on is some kind of agent-based autonomous adjustment in which, like, for example, you can even do like even more granular in time optimization of the trigger. So like, for example, with like changing conditions, for conditions that change very fast, like the pileup, for example. And yeah, this brings me to my conclusion. I want to conclude that we're working on many of these things also with the next generation triggers project at CERN. This has been, so this was founded by Eric and Wendy Schmidt Foundation. They gave us like a lot of money to do like this thing, to indeed build like next generation triggers for LHC experiments, but there is also a lot more. Theorists also are being involved here, and we discussed with them also like about new ideas for theoretical models that can be accessed through anomaly detection in the trigger. And yeah, so that's one last thing is that we're hiring right now, especially for foundation models, the ultra-fast foundation model idea for phase 2. Here's the link. Unfortunately, the deadline is like just today. But please look at the pages that I linked because we put usually here the positions. And yeah, we hire for these things. And thank you. Bye.
Any questions?
Well, I can think of two cases. One, find an anomaly. In either case, you have to determine either a limit of some process, or if you find something, you have to measure cross-section, angular distribution. It says, how do you determine the systematic uncertainty of doing that?
So in the digest search that I discussed before, so we just like basically like shifted like, for example, jet energy scales, jet energy resolutions up and down, and then rerun the network. It's a very complicated process, but we basically did it like as any other algorithm. Like, just like your cut is not like on an actual just one variable, right? It's about a neural network that uses many variables. So otherwise, it works exactly the same as normal. Yeah. Does that make sense? As because you have some signals, right?
The hadronization models that are used to analyze the events are not, they're heuristic, not based on QCD from first principle. But those models were improved, or if you had some guarantee that they're accurate to a certain level, would that improve your ability to identify and interpret anomalies?
Well, so here we're talking also again like when you're putting limits at the end, right? Because that's when
QCD more accurately so that you can identify anomalies that you might otherwise miss.
But we don't train on Monte Carlo. So we train only on data, right? So the Parton shower model only matters when you start putting limits on signals.
data.
How to use data.
You need to, so you don't think it would make any difference? The models don't matter in identifying a model. The head and the makes no difference.
No, that makes only if you use Monte Carlo. That matters, right?
Models are sources.
Yes, they are. Yes, indeed. When we put limits, then we take that into account, and then we do different hadronization of the signals, and then we count that as systematic. So we do, like, for example, PT and R rig for different signals, and that's our systematic, and then we see how the signal efficiency changes, and that's how we put limits. Yeah, but.
Another paper. We showed many algorithms, and so the pattern that what looks like anomaly is actually a limitation of the algorithm, and how do you know that?
What looks like an anomaly is a limitation of the algorithm. So you're basically saying that, yeah, that's like the hallucination basically I was talking before, right? That like the algorithm sees something that's anomalous, but actually it isn't. Yeah, that could happen. That could happen. So we did indeed an extensive validation for particular for the digit analysis. We did. So we tested the algorithms in a control region, making sure, because in particular we do bump hunts, right? So okay, I don't think probably I didn't put the plot, but so we fit a smoothly distribution, basically exponentially decaying distribution. So we checked that distribution is not sculpted by applying a selection on the anomaly score on the neural network, basically. So because indeed that was why the first thing we thought, it might invent some bumps, it might invent some structures because it's hallucinating. So we had to check that, and it didn't happen. But there are techniques though that you have to apply during the neural network training, indeed, to make sure that doesn't happen, to make it robust.
Actually, oh, okay. Question about the first operation. So you compress and update the different class. And how do you compare the result with the data?
Yeah, with basically the mean squared error between the input and the output. So yeah, so that's an example, right? So that's an autoencoder. So you put your whatever images or representation of your events, and you compress it, and then you reconstruct it. You reconstruct it from this compressed latent space, and then you compare the reconstruction with the input. So your anomaly score is actually like the difference between these two, the input and the output. Yeah.
If you don't do force training, producing some metric.
So I mean, when you train it, so basically you train it on the background only, right? So that you want to minimize the difference between the input and the output, because you want to learn to reconstruct very well this background. Okay? And what's anomalous is like new stuff. Dead. Yeah. Yes. No, yes, it's lossy. It's a lossy compression, of course. So you won't get a perfect reconstruction. Does that make sense? That's the question. Okay. I didn't understand.
So a little off topic, these techniques you've developed to get the algorithm to run on FPGAs, including using number of bits and so on, it seemed to me that those techniques have wide applications outside of what. Is there any interest in other communities and practice that has been taken up in other areas?
Oh, yeah, I mean, so like particle physics, there is more than LHC. Yeah, so like I am actually, yeah, even above, yeah, yes. So actually, we built a full community around this. We call it fast machine learning. We have like workshops every year, and there's also like our industries there. There's Xilinx that we were AMD. They work with. For example, that's one of probably the biggest partner that we have, because there is interest, of course, like for any like edge device, like your Apple Watch or satellites. Also, like for example, because you have low power and satellites, especially when you have low power, you want low power and speed at the same time. Then, of course, LHC is particularly I say challenging because we are really going to the nanoseconds, microseconds latency. So like I think in industry, or like I say in normal life, it's you're more like maybe in the milliseconds or so. So we're particularly challenging that. There's still also like nanosecond level applications of these, like for example, for finance, for trades, and any like also else devices. So I think yes, there's plenty of applications. So we didn't completely invent it, but we wanted to make it custom in a way that we have, because when we started this, so industry doesn't come with a generalizable tool. They come with specific, maybe other specific tools, like their own, like maybe one algorithm that is needed to do that exact thing, right? So instead, we wanted to make it as general as possible because the applications in science are actually way broader, I would say.
Nothing around.
Yeah, we had to do it ourselves. Yeah.
I have a very naive question. So let's say we get lucky or nature is kind to us and you discover an anomaly, non-standard model. So I guess the way you're doing it now, it knows the events, right? Those events are written to tape and then go look at it with more conventional methods. Is that correct?
Yes, that's what we're doing now as a first approach. So we take this data set and analyze it with conventional approaches. But I think what would be actually very interesting to do is like making a catalog, like a catalog of anomalous events. And like, so yeah, so like look at them kind of one by one, but in an automatized way. I don't know if that makes sense.
You start off with this method. And then, so you had the example when it was just QCD at the ZP. So something else is found, not in the standard model. But then what I'm asking is, then you still have those events written to tape, right? You can go back and use the methods from 1980 or
Oh, yeah,
whatever and make sure it's not a hallucination.
Yes.
Trigger.
Well, if you, so, okay, so
Yeah.
your analysis is, not everything is written to tape then?
Yes. I mean, based on a threshold, right? So we set the threshold based on the bandwidth that we have downstream. So like CMS decided to give us 250 Hertz. So, but it's still like quite a big data set.
This has to then link your level 2 triggering system. That decides what's being saved.
That's a good question. Now we're doing pass-through. Yeah. So at HLT, nothing happens. So that's why the threshold is very, very tight at 200 Hertz, because we don't do any HLT strategy. Now for 2026, for next year, we're progressing on having level 1 plus HLT. So at level 1, you can be like way looser. At HLT, you can do something better. To kind of like clean up even better your sample. Yeah. But yeah, step by step.
Okay, why don't we thank Jennifer again for a great talk?